All right. So what I want to do this week is to actually go into the actual meat of the topic, where we had, charge densities, currents, electric fields, magnetic fields, all the things we did before, but now get a relativistically proper formulation for them. Of course, the way we'll do it is, the easy way out, which is try to define new four vectors, right? I mean, that's always been the easy way for us to apply Lorentz transformation. So let's have a look at a few four vectors. So I'm going to first define something called the four current. And how do you actually build a proper four vector? So, so charge density times velocity is the current density, right? And you know that something like the four velocity, right? So can we get a four current which is kind of similar to the four velocity? So in other words, can we use the four velocity and multiply with some Lorentz scalars and try to get a four current? Now the four velocity is this, which is derived this last week, right? Gamma times c and is the time-like, and gamma times v is the space-like component. Now, let's say I'm going to multiply it with rho naught, which is a Lorentz scalar. So I still get a valid four vector. Now, to make sure that rho is a Lorentz scalar, or rho naught in this case, I have to define it such that it's the same in all frames. So I'm going to define it as the charge density in a frame where the charges are instantaneously at rest, okay? It's a little bit like rest mass, right? I can't just call it rho. It has to be in this special frame, because densities are not going to be the same in different inertial frames, just because of length contraction, basically. Okay, so I'm going to multiply the whole thing with rho naught, and I get something interesting. So gamma times rho naught is actually the charge density in this frame. By this, I mean the frame in which you're constructing the four vector. Okay, so in this frame, you're watching the charges move at a velocity v, right? So v here is the velocity. So you're not in the rest frame of the charges, you're actually in some other frame watching the charges go at velocity v. So in that frame, one of the length axis is going to Lorentz contract by a factor gamma. The other two axes are not going to undergo contraction. So the charge density, so charge per unit per unit volume is going to basically be gamma times rho naught, where rho naught is the charge density in the rest frame of the charges. So gamma times rho naught is just the charge density in the frame in which you're defining the four vector. In a similar way, gamma times rho naught is the charge density times the velocity. So this is the current density in the frame in which you're defining this vector. So you can actually have a four current, which is c times rho times j, where as long as j is the current density in some frame and rho is the current density in the same frame, this becomes a valid four vector. And so now you know how to transform charge density, you know how to transform current density, because now you've just put it into the form of a four vector. Okay, so it's not enough to just have the charge and current densities. If we go to Maxwell's equations, you have all of those differential operators. So what happens to the differential operators? Well, we need to now define something called a four gradient. So we need to know how to transform these curl, divergence, and all of these differential operators between frames. So you know what a three gradient is, right? This operator is just the three spatial axes, partial derivatives along the three spatial axes. And using this, you have created a whole algebra, right? We have curl, divergence, gradients, Laplacians, all of those things. This comes from this basic operator of spatial derivatives, partial derivatives along spatial axes. So now we're going to have a new operator, which is analogous to that, but with two differences. One is you're going to have a time-like component, and of course, to get the dimensions right, I'm going to put a C here. And I'm going to flip the signs of the space-like components. And the sign flip is important because of the way we do algebraic operations in the four vector notation. So when you take the dot product, you always put a minus sign in front of the space-like quantities, right? So to have everything come out consistently, as you'll see soon, I need to define those negative signs here. Now, suppose you have some kind of a scalar function, phi, okay? So it's a function of, let's say, x and t. I'm just taken it at one spatial dimension for simplicity. It just generalizes to other dimensions. What you're really doing with the gradient is you're trying to do calculus of variations, right? You're trying to see what is a small variation in phi look like. So, this is a fundamental theorem in differential calculus. So if phi depends on two independent variables, so a small change in phi is going to be the partial derivative with respect to one variable times the differential change in that variable, and the same with the other variable, right? So I've just written down a basic theorem in differential calculus. Now, what I want to do is I want to actually see how to calculate the differentials in the primed frame, in some other frame, okay? So I'm going to for now assume that phi is a Lorentz scalar field. So it means that d phi is going to be the same in another frame, okay? So in that frame, I can basically write exactly the same equation, right? So instead of unprimed variables, I have the primed variables. Now I know how to transform dt prime, right? So I know the Lorentz transformation. So dt prime is just gamma dt minus gamma beta by c times dx. Notice there's a minus here because you're going from prime to unprimed frames. Yeah, the same with dx prime. Okay, so I can write that out. So now I have a scenario where I can kind of relate these two, right? So I'm going to try to find the transformation between the operators themselves. So the way I'm going to do that is actually write down if you actually write down d phi by dt using the d phi by dt in these equations. So if you look at d phi by dt here, if you look at this equation, d phi by dt is just the coefficient in front of dt, right? So I'm going to collect all terms with dt over here, and there's another term here. Then I get d phi by dt as the coefficient in front of them. I'm going to collect all terms with dx, so which is this term here and this term here, and the coefficient in front of that is going to be d phi by dx, right? So I can basically do the algebra, and then you can pause the video and check things here. I get d phi by dt in terms of the derivatives in the primed frame. So those are the kind of Lorentz. This is the way to Lorentz transform a differential operator. Okay, so it's just instead of Lorentz transforming a physical quantity, you're transforming an operator, right? In this case, the operator is the partial derivative operator. So basically, based on this, you can write down a Lorentz transformation, which for a pure boost along X looks like this. Now, if you define your 4 vector as, so I'm going to now just drop implicitly the phi here, right? It doesn't matter what that function is. I can actually get a transformation for the operator itself. The idea is to get a transformation for the operator itself, right? That's the main point. And so I can write a new, I can just say that, I'm going to just say that this is a 4 vector, right? So instead of this being an operator, I'm just going to say it's a 4 vector, right? I'm going to just treat it like a 4 vector, even though it's really an operator. But for the algebra case, for the sake of algebra, I'm just going to treat it straight as a 4 vector. And then what this equation is telling you is you can actually transform the 4 vector in a way you just transform any other 4 vectors, right? So you can just do the same kind of transformations. Of course, in all of these, you need to worry about the signs, right? Because in your definition of 4 vector, you've included a negative sign. So you need to make sure that those signs are properly taken care of. But when you do it, then you get this kind of transformation. So you say, this is a partial derivative with respect to time is of any quantity, it doesn't matter, of any field here, is equal to gamma times partial derivative with respect to time in a different frame, in the primed frame, plus beta times the partial derivative with respect to space in the different frame, right? So I hope you can understand the trick here. We are literally doing Lorentz transformations of operators, of differential operators. So if you have a differential operator in one frame, you can actually convert it to a differential operator in another frame. And we need all of that because Maxwell's equations has all of these differential operators, right? It has these curls, divergences, and all of those things. So we need to have an algebra to deal with it. And so the idea you get is that this is just a 4 gradient. This is called the 4 gradient. And putting it in this notation enables you to actually transform the gradient operation from one coordinate or one inertial frame to another inertial frame. So if in one inertial frame, you just have a simple derivative with time, when you go to another frame, you're going to have to take this more complicated derivative with time and with space, okay? So you can literally use this like an algebraic quantity and then transform things between frames. Even though this is not a physical quantity, it's actually an operator, but you can write it out algebraically speaking this way. And it helps you to, it gives you laws to to carry over differential operators to different frames. Now, of course, what you get immediately from it is, the 4 gradient of any scalar field, which we took as phi in this case, is going to be a valid 4 vector. Okay, so that's one way to just construct valid 4 vectors. Anyhow, because this was just a pure operator and nothing else, you can also take the 4 divergence. It doesn't have to be a 4 gradient. In which case you just take this operator and then take the dot product or the scalar product. Let's take a 4 divergence of the current, right? So this was the 4 current, C times rho, comma J, this is the 3 current. So let's just take the dot product. Notice that in this notation, when you dot, you need to flip the sign of the space-like quantities, but there's already a negative sign on the operator. So those two cancel and give you positive sign. So I mean, a note here is basically be careful with signs when you're using the 4 divergence operator. Just notice the sign flip there. It often gets confusing. Before you get used to it, of course. Once you get used to it, you'll get it right. But just pay attention to the signs. Okay, so you write all of that out. You get partial derivative of charge density with time plus divergence of the current density, and you know that has to be equal to 0. This is just the law of conservation of charge. It just says that divergence of the current is basically the amount of current leaving a certain point, right? That's what divergence is. It's the amount of current that is leaving a certain point that has to correspond to an increase or decrease in the charge density at that point, right? It just says that charge is conserved. And so one of the things you should do is the moment you see a 4 vector, take its 4 divergence. The reason for that is you usually get some kind of a conservation law from it. So in this case, you get, if you take the 4 divergence of current, for current, you get the conservation of charge. Also notice it's 0, so it's a Lorentz scalar. That means that charge is conserved in all inertial frames. And that agrees with your intuition, right? Anything that has to do with total number of discrete entities is always a Lorentz scalar. Anyway, yeah, so 4 gradient typically gives you conservation laws. So you can build some intuition by taking 4 gradients of different vectors. Now, like I said, we cast all of these operators as if they were just algebraic variables, which means that we can also take, concatenate them together. Just like you would dot 2 vectors, you can dot 2 operators. And so in three dimensions, in normal vector algebra, you just did that with the gradient and then got the Laplacian operator, right? So I can do the same now with the 4 vectors. So I can take the dot product now. So notice that, oh, sorry, there should be a minus sign here and here. So all space-like quantities should have a minus sign. I've missed 2 of the minus signs here. Okay, so now we are going to dot them. So when you dot them, the 2 minuses go away, but the dot product rule requires you to put another minus in front. So yeah, so pay attention to the minus sign. So in the end, you'll have 3 minus signs multiplying and you get the minus sign ends up here. So anyway, the Laplacian is now going to look like second partial derivative with time, and this, the normal 3-dimensional, the 3 Laplacian. What's interesting about it? Well, if you remember from last week, this looks an awful lot like the wave equations we had, right? Second derivative with time, second derivative with space. So what's really interesting is if I now take this Laplacian operator and if I apply it on let's say phi and a, okay? So let's say phi was the time-like quantity of a 4 vector and a was the space-like component of a 4 vector. And if I hit that 4 vector with this operator, then I'm going to basically get these 2 equations, right? So the left-hand side is just the time-like component, right? And the right-hand side is just the space-like component of going through this operator, right? So I'm just, taking the Laplacian of some 4 vectors. So that this equation is basically what we derived for the scalar potential relationship with the charge density and the vector potentials relationship with the current density. Now you can write the whole thing in a compact form. You can just say that the Laplacian of phi comma a is just equal to minus 4 pi by c times j, where j is the 4 current, right? I'm just taken these 2 equations together. Okay, that's all I've done. So when you take the inner product of these 2 4 vectors, you get a scalar, right? This is not a vector, this is a scalar. because you've just taken the inner product of two vectors. And now this is a scalar operator. Okay, don't forget it's an operator. It's not a physical algebraic quantity. It's actually an operator. So it operates on objects. Yeah, so you basically get these two equations in a compact form, which now means that phi and a must be a 4 vector, right? We're doing 4 algebra here. Everything is 4 algebra. All operations are on 4 vectors, which means that phi a is a 4 vector, and that's called the 4 potential. Okay, so now you know how, now you're done with charge, current, the scalar, and the vector potential. They all neatly fall into a 4 vector, right? You know the 4 current, and now you know the 4 potential. Now, like I said, whenever you see a 4 vector, take its divergence. So what happens if I take the divergence of the 4 potential? I'll leave you to do the algebra here, but essentially you get a quantity that looks like this, which we set equal to 0 in the Lorentz gauge, right? If you remember, we had different gauge fixing. We went through different gauge fixing, and one of the gauges was the Lorentz gauge. The nice thing about the Lorentz gauge is that the 4 gradient of the 4 potential is 0 in the Lorentz gauge, which means that this must be true in all inertial frames, because 0 is just a Lorentz scalar, right? So that means that in any as long as you work with the Lorentz gauge, your 4 vector, your 4 potential is going to have a 0 divergence in all frames, right? And that's why the Lorentz gauge is quite popular, because it just makes the algebra a lot more simplified when you work with 4 vectors. Anyway, that was a quick aside about how you take the 4 divergence of vectors. You usually discover something interesting when you take the 4 divergence of 4 vectors. Okay, so now we need to get to the electric and magnetic fields. Okay, the unfortunate thing is there's no such thing as 4 electric or 4 magnetic field, right? There is no, it turns out that these cannot be captured as a 4 vector. In fact, the electric and magnetic field will become part of a tensor, and we could do all of this in tensor notation, but I don't think we need that for the rest of the course. So I don't want to introduce a new type of notation here, but I want to show you how you can actually now Lorentz transform the electric and magnetic field, right? So far you know how to Lorentz transform all the classical things like, you know, position, time, momentum, force, acceleration, and now you have learned how to Lorentz transform charge density, current density, scalar potential, vector potential. Now we are only left with 2 things. We need to know how to Lorentz transform the electric and the magnetic field. So that means that we need to now see how I relate the transformation of potentials to the transformation of fields, okay? So we know how to transform the potential, so let's start there. So B is just curl of A, so I can write that out fully. So Bx is just going to be A of AZ, the Z component of A, partial derivative with Y, minus AY partial derivative with Z, right? That's just the definition of curl. Similarly for By and similarly for Bz, right? So I'm going to use this shorthand here. And this shorthand, you know, this, at least I learned and a quick shorthand here from Feynman lectures. That's where I've taken some of this material from. Things become, you know, quite simple when you have the shorthand. So I'm going to call this some FYZ, right? FYZ just means this. Okay, FYZ literally means I'm taking this kind of operator on the potential A, vector potential A. Now notice that I call it YZ because it only depends on Z and Y coordinates, right? There's no X in it. Like anything varying with X has nothing to do with this quantity here. So similarly here you get, you know, F of ZX, F of ZY. Yeah, so, you know, you can kind of write these things out. Now, let's see, every time you saw 4 vector, the space and time-like components were together, right? I mean, that's what made a 4 vector. A 4 position had space and time-like quantities together. So is there something like f of xt, right? Where x is a space like quantity, t is like time. So what would that look like? That would basically look like partial derivative of a t with x plus partial derivative of a x with t, okay? And let's see what this actually is. Now, partial derivative of the field with time. Where have you seen that before? Well, you've actually seen that in the relationship of the electric field to the potentials, right? So the electric field is some kind of a partial derivative with space of spatial coordinates and the partial derivative of A, which is like a time-like coordinate. So that means that, the partial derivative of A of t with time, so, f of xt must have some relationship to the electric field, right? So it looks like f of xt is related to the electric field. So let's see in which way. Now, the partial derivative of at with time, okay, so that is just the scalar potential here, the gradient of the scalar potential, right? Because this is the time-like component of the, let's say A was the four potential, four vector potential, right? So A of t would just be the time-like component. So I can, define A of t as just phi. Okay, so this just becomes d phi by dx plus A of x partial derivative with t. Okay, so I just leave it here. Now, if you look at this equation, it looks exactly like this. It looks like the x component of this equation, right? So E of x would be partial derivative of phi with x minus 1 by c, partial derivative with time of A of x, right? So that's exactly the x component of that equation. And how did this become the x component of that equation? Well, by just recognizing that the time-like component of A must be the scalar, the scalar potential phi. Okay, so we know that f of xt is minus of E of x. Okay, so in a similar way, f of yt should be minus ey and f of zt should be minus ez, right? So that much is clear. So just, you can pause the video here. So, just have a look at it. So, things are clear to you. Okay. Oh, by the way, I think this should be bz should be f of xy. This shouldn't be z. This should be x, I think. Yeah, this should be x and y. Okay. Okay, so now you know how to go from one four vector to the other four vector. We are almost there, right? So we kind of have a relationship between phi A and E and B. So I can just keep doing this for all the other axes. And in the end, I'll end up with something like this. I'll end up with Bx is f of yz, By is f of z x, and Bz is f of xy, Ex is minus f of xt. So when you have the time and space things combined, you get the electric fields. Ey is minus f of yt, Ez is minus f of zt. Okay, so now we have related the components of the four potential to the electric and the magnetic fields, and now we need to do the field. We need to do the actual transformation. So now we need to go from one frame to the other. Okay, so we know how to relate these two in the same frame. And now we need to actually go from one frame to the other. So we need to basically take these operators, these differential operators, and go from one frame to the other. And you know how to do that. You know how to transform differential operators. So the whole thing is going to become really messy and cumbersome. So I'm going to do just a couple of terms here. So let's say I want to look at f of yz prime. So now I'm in the primed frame. I want to come back to the unprimed frame. So in the primed frame, I'm going to write down exactly this equation here. For f of yz. Okay, so I'm just writing this equation in the primed frame, and I'm going to just assume that there's a Lorentz boost along the x-axis. Okay, so partial derivatives with y and z are going to be the same. There's not going to be no change. Again, because the boost is only along the x-axis, when you Fourier transform the four potential, nothing is going to change along the y and the z axis, right? So this is very easy. There's no dependence of anything on the x-axis or on the time coordinate. So f of yz prime is just f of yz, right? So that's easy. That means that bx is just bx prime. Okay, what if we have a coordinate where Lorentz transformation is important? So let's take f of xy prime, which is that's just the definition in the primed frame. But now I need to worry about transforming the d by dx prime operator, right? So I have a partial derivative with x prime, but you know how to transform the operators. This is just the transformation of a four gradient, right? So d by dx prime just becomes this operator here. So partial derivative with x prime becomes this more complicated derivative in the unprimed frame. Okay, so ay prime is just going to be equal to ay in the end, because the Lorentz boost is only along the x-axis. It doesn't affect the y and z components of four vectors. Now the partial derivative with a y prime, partial derivative with y prime is just going to be the partial derivative with y, because there's no Lorentz boost along the y-axis. So you get something like this, right? So you can rearrange this whole thing. So let's see what you get when you rearrange the whole thing. Again, ay prime is just ay, so that term is taken care of. Everything is now in unprimed coordinates. Now ax prime has to now be Lorentz transformed, right? To go to the prime, to the unprimed coordinates. And you know how to do that. Ax prime is just the first element of a 4 vector. So you know how to Lorentz transform the first element from the primed frame to the unprimed frame, okay? Again, the minus is here because you're going from prime to unprimed frame. Okay, so you can basically, rearrange all of that and you end up with this. Once you rearrange all of those derivatives, you kind of end up with this Lorentz transformation. So f of xy prime, which we are trying to evaluate, this is going to be its Lorentz transformation. It's going to be gamma times f of xy plus beta times f of yt, okay? So all of these are just coming from these partial derivatives here, right? What does it mean? F of xy prime is bz prime, if you remember. F of xy, yeah, here, f of xy prime was bz prime, right? So what does it mean? So bz prime is gamma times bz minus beta times ey. F of yt was ey. So now you have one component of the field transformation. So you can keep doing that. There's no point doing it for different components. I'm just going to write the final expressions here. You'll see that the x component of the fields do not change at all. This is for a pure boost along Lorentz boost along the x-axis, and the y components of the electric field is going to involve the z component of the magnetic field. When you Lorentz transform, the y component of the magnetic field is going to involve the z component of the electric field. The z component of the electric field involves the y component of the magnetic field. Z component of the magnetic field involves the y component of the electric field. Yeah, so these are the transformations of electromagnetic fields between two frames. As you can see, they don't look like very simple Lorentz transformations, right? None of these look like simple Lorentz transformations. And that is the reason why we don't have a 4 electric field or a 4 magnetic field. It just happens that electric and magnetic field transform differently. They just don't transform like simple 4 vectors. You can write it in a compact notation. If you have like a parallel component, so parallel to the Lorentz boost direction, in which case, in this case it was x, but you can just have any axis. Parallel to the Lorentz boost, the electric and magnetic fields don't change between the two frames, and perpendicular to the boost, you can notice how, z component of electric field depends on the y component. So, you already know that there's a cross product involved, right? Because the Lorentz boost is along x, so x cross y gives you z. So you know that you can kind of write it in this notation. So the perpendicular components are gamma times, the same field. And if you're doing electric field, you get the same electric field plus, beta cross the magnetic field. And similarly, the magnetic field is going to have a beta cross the electric field. And, there's a sign flip. Yeah, so these are the Lorentz transformations of the electric and magnetic field. Well, one of the nice fundamental thing that tells you is that there is no such thing as an electric field. And the reason I say that is, you can see that when you Lorentz transform between frames, electric field and magnetic field are related, right? Like, so it means that if you say that, oh, I have some electric field here and no magnetic field, that only makes sense if you also tell me which frame you're talking about, right? Because I can go to another frame where you have a magnetic field. You just generate a magnetic field from Lorentz transforming the electric fields. And that's why, just like there is no separate time and space, they're both related. In the same way, there's no such thing as a pure electric or a pure magnetic field. And that's why we call it electromagnetic phenomena, right? There is only an electromagnetic field, just like there is only a space-time, right? There's no pure space or pure time. In the same sense, there's no pure electric or magnetic field. There is just an electromagnetic field. And this is how you Lorentz transform the fields.